Okay, so this is the final assignment. First, location, it's in Manchester, New Hampshire. Okay, so I have decided the location, and I have pasted here so you don't have to look for it, so to look it up on the internet. I have pasted January the 21st, which is the coldest day. And here you have the temperatures, the daily temperatures, and the relative humidity. This is winter, and this is summer. So July the 21st is the day with the highest temperature above 95 Fahrenheit. Okay, so here you have the temperature and relative humidity. So this is the location, and this is all we need. We need the coldest and the hottest day, the temperatures and relative humidities. We have a building, and you have a Revit file, so you can take measurements on that Revit file. And this is the statement. So there are three different things that we have to do. Well, there is actually a fourth one. The fourth one is the electrical. But for the electrical systems, we don't have to draw anything. We just have to calculate. So I will upload it later. So what do we have to do? For the mechanical systems, we have to calculate the ventilation airflow. We have to calculate indoor and outdoor enthalpy. We have already done this. And then we have to calculate the heating power in winter, the cooling power in summer. And this is the schedule of system operation or the building operation. So we have, this is an educational building. We have classrooms and offices. So it's something similar to the TDS building. And the schedule of classrooms, it's from 8 a.m. to 1 p.m. Then we have 2 hours without any activity. And then from 3 to 8 p.m. So we have 5 hours in the morning, 5 hours in the afternoon or evening. But the offices are occupied from 7 a.m. to 8 p.m. Okay, so this is the schedule of classrooms. And based on that schedule, we have to calculate the total daily energy in summer and winter. So first we need the heating and cooling power, and then the energy. And then we have to draw the schematics of the building. It's something similar what we have done so far, but everything is electric here. Okay, so on the first assignment, we worked with a condensing boiler, but here everything runs on electricity. So we have electric water heaters. We have an air-cooled. It's not a water-cooled, so we don't need a cooling tower. So it's an air-cooled chiller. The air handling unit. The air handling unit has a heat recovery, 50%. The efficiency of the heat recovery is 50%. And then finally, we have a split system. And the split system is made of the air-to-air outdoor units and indoor units with ducts. Okay, I will explain this today. So this is it. We have to calculate, but calculating is just, it takes 10 minutes because we are going to use this Excel file, this wonderful tool that I have created by myself. So that's why it's wonderful. And by using this, it takes minutes to calculate the heating loads, the cooling loads, and the energy that we need. Okay, so and then you have to create the graphic. So I haven't inserted the graphic here. You have to do it on your own, but you know how to do that. So you only have to change the indoor temperature, the outdoor temperature for winter, summer, the number of people, that's important. And by changing indoor and outdoor temperature and relative humidities, and the number of people, everything is done here. It's calculated here. We will talk about this later. Okay, so this is the mechanical system, and this is what we have to do. Then for the cold and hot water supply, we have to calculate the water supply fixture units. If you open the Revit file, you have this information here. So we have 2 floors. This is level 0, and this is level 15. Okay, so there are 2 floors. They are the same. So when it comes to the water supply fixture units, so this toilet, if you click here, we have 6. In this sink, we have, okay, 2.25, 2.25, 2.25 water supply fixture units for the hot water and the cold water. Okay, so, and these are the only fixtures we have. We have sinks and we have toilets. So how many fixture units? We have four toilets times 2 floors. So there are 16 toilets and 16 sinks or lavatories or whatever. You don't have to go over the table because Revit provides us with this information. So here each sink has 2.25 fixture units. So the first question, the water supply fixture units, we have 16 toilets, 16 lavatories. So this is just number, whatever. Then calculate the maximum developed length of water piping. We have to multiply the actual length to the most remote fixture by 1.2. Okay, so here we have to understand the building. So the cold water supply will be on the basement. Okay, so on the basement, we have a heater. And from this heater, we have to supply water. As you can see, we have the cold and hot water supply. And here we have a shaft. Okay, so all the pipes, the water pipes, have to go through this shaft here. Okay, so this shaft on the Revit file, it's here. Okay, so this is, I think, on the 3D view, or even if we work with the architectural discipline. Okay, so as you can see, we have this floor. So those elements are vertical shafts, or these, there is no floor here, there is no slab. Okay, so you can go up and down through these shafts here. So there's another one here, and there's another one here. So you can go up through this element. So it looks like a room, but this room is, there are a lot of pipes here. Okay, so we open that door and we can access all those pipes. There is no room here. Those are locker rooms, can be storage or locker rooms or whatever, but this is just a shaft. So it's filled with pipes. If we have the water heater here, or if this is the mechanical room, so we are going to use this shaft, and we will use the other shafts that you can see for the air ducts. Okay, so the shafts that are here close to the elevator, and this one, it's close, well, it's in the classroom. So we will use this for the air ducts, but we will use this shaft here for the water pipes. Okay, so somehow we have to connect this domestic hot water or the water heater to the farthest fixture that can be, yeah, so probably this toilet will be the farthest one, because if the hot water tank is here on the basement, so this is level -15. Okay, so this is the mechanical room. You can place your water heater somewhere here. Okay, and then you have to connect this to the farthest toilet. We can do this easily. So if you, this is in the toilet, we have the drainage and we have the water supply. So this is the water supply. This is 1 inch. And this is 4 inches. Okay, so this is the drainage, the symbol. And this is the, okay, so we can do that. We can draw pipe. And here, it's good that we can change the elevation. Okay, so if we go this way, you know that we have to come from the ceiling. Okay, so if we change the elevation here, it can be, let's say, 10 feet. Okay, we don't see it because of the visibility range. but we have to go all the way to this shaft. And then if we change the elevation, if we know the project, we can just type here, this is 10, let's say negative 20. And then we can continue. So let's see what we have done. Okay, there you go. So if you know the elevation, so we know that it has to come from the false ceiling. Okay, so that's why I have I don't know, the false ceiling can be here or higher, I don't know. But just by clicking here and using the elevation, we don't need anything else. And then I know that I have to go down to the basement and the water heater will be somewhere in the basement. Okay, so by clicking all these, I think we can, is it the length? Where the hell is the length? Okay, so the length is here. Does it work if I select it? No, it doesn't work. Okay, so I have to go one by one. So this length, it's around 13, 14 inches. This length, it's 29. This length is 109. Okay, so this is the distance from the supply, from the water heater, or where the pump is, to the farthest fixture. Okay, so this is what you have to do. And then you just have to type here the maximum developed length. It's the actual length taken from Revit times 1.2. Why times 1.2? Because we have all these fittings, the elbows, the T's, and well, we have to do that. Okay, so there's, if we didn't have any T or any fix or any fitting, it would be the actual length. But since we have T's, elbows, and all that stuff, we have to multiply this by 1.2. What is the static head in PSI? So it's the maximum height that we have in this. Okay, so the water supply would be underground. So if this is level negative 15, so what is that length? Annotate. Oh, because I need the elevation. East elevation. So from this point to that point, the maximum length, it's around 40 feet. It can be 40, 41, 42, something like that. And then here, the static head or the pressure loss, it's 0.433 times the maximum height, which is around 40 feet. Okay. So with this, with the water fixture units with the maximum length, then you have to calculate the minimum meter and distribution pipe sizing. The minimum. Okay, so you remember that we have this table. No, this is not this table. This is the sanitary. We have the piping. So with this table, the last one, okay, depending on the pressure loss, depending on the maximum developed length, then we calculated this, and this is the minimum. So now we have to check if this minimum is enough, because we have other rules of thumb. Okay, so you remember this, that up to 5 3/4 inch branches, or up to, okay, so we need this. So you have to check. Okay, so by in Revit, you will have a default pipe. and the default pipe in Revit is 1 inch. Is 1 inch enough? Well, I don't think so, because we have up to 8 toilets here, 8 toilets there. So 1 inch, it's enough for maybe for this branch. But if we are adding different toilets to the same branch, then it wouldn't be enough. Okay, so I want you to calculate based on the fixture units. I want you to calculate the size of this first pipe, which is from this, no, from this one, this table. No, this table. Okay, the maximum pipe here is 2 inches. So 2 inches should be enough. So you have to find out if it's 1¾ is enough or 1/2. I don't know. I think it will be close to 2 inches, between 1¾ and 2 inches. Anyway, you can spend 5 minutes of your lifetime doing this. So once you have the total length, then we only need to add up all these fixture units. And then with this table, we have the height. So with this table, we need to calculate the minimum size of this pipe. Okay. So with this, we are done. Okay, so water supply fixture units is just counting the fixture units that we have for toilets and sinks. The maximum developed length, I told you, well, I haven't calculated it, but you have to add all these segments up, and then the total times 1.2 is the total length. The height is, yeah, it's around, this is around 40, 41, 42 feet. And with all these values, you have to calculate that. So that's it. For the drainage or the sanitary system, we have to calculate the drainage fixture units. So again, if you click on this toilet, so we have 4 fixture units. So there are 6 water supply fixture units, but there are only 4 drainage or sanitary fixture units. Okay, so that's different. 6 for the water supply, 4 for the sanitary. And what else do we have to, well, and for the sinks, this is 1, no, this is 2 fixture units. Okay, so each sink is 2. So 4 for the toilets, 2 for the sinks, times 16 toilets times 16 sinks. So you have the total drainage fixture units. But now I want you to create 2 different systems. So there's a system for the storm, the rainwater, and the gray water. So the gray water is coming from the sinks, and we need another system for the sanitary. Okay, I told you that nowadays it's almost mandatory. We cannot mix a sanitary system and storm or gray water. We can even have 3 of them. So we can have a system for the storm water, another system for the gray water, and a different system for the sanitary. But I think 2 is it's enough in this exercise. Okay, so now the number of size of storm stacks. So we have this building. Okay, so looking at this building, if we select the roof area is 9,809 square feet. Okay, so I don't recommend you have only 1 storm stack for this area. It's almost 10,000. Yeah, it's 10,000 feet. So now we have to make decisions, but we have to make decisions based on the shafts. Okay, so if you see that we have shafts here, all these rectangles, this one, this. So those are shafts. So through these shafts, we have to place the storm water that comes from the flat roof, because we have a flat roof here. So how many, if we divide this in 4 sections, so 10,000 divided by 4, okay, so we can say that 10,000 square feet divided by 4, that will be 2,500 square feet. Okay, so that means that we have 4 storm stacks. It can be 4 or 5. Well, I have decided 4, so now I have to check if that decision is good or it's not good. Okay, where are we? We are in Manchester, New Hampshire. So the rainfall intensity, it's around 5.4. Okay, so it's around 5. So if we are here, if we have a rainfall intensity of 5, our square feet for each sector, it's around 2,500. Okay, so if it were, yeah, so it's between 3 and 4. And this is what I told you, that it's reasonable. Okay, so we can divide this by 5. So we can have 5 storm stacks, and each one would be 2,000. So if it's 2,000, it's the same. So it doesn't make any difference. It can be 3. If it's 4, it's even safer. You would have less risk of jams in the storm water, but 3 or 4 inches, it's fine. Okay. And now the place, if there are 4, so we can have 1 here, 2, 3, and 4 in this shaft. Okay, so I don't mind. We can be 1 here, 1, 2, 3, and this is the 4th one. I know, but we need 4 storm stacks that go from the roof in this section. Okay, so those wherever the shaft is, so we need to go all the way down, and usually we go, because on this assignment on the basement, so we have the storm sewer and the sanitary sewer. Okay, so there's a horizontal pipe that comes from the toilets to the sanitary sewer, and there is another horizontal pipe that comes from the sinks and the rain stacks to this storm sewer. Okay, you have to design it, but when it comes to calculations, we have already done it. Okay, so with this, if you want to be on the safe side, make it 4. Okay, so there is no, it doesn't make any difference. So from yeah, make it 4, and it will be, you will be on the safe side. What else? And then we have to design the system. If we are designing the system, looking at this east elevation, yeah. So for the sanitary system, there should be a trap here in the toilet, and then we have to go down, but we have to go down beyond. This is the slab, you see, so we cannot go through the slab. So we have to go down up to this point, and then we have to go to this shaft, or to this hollow. So we have a wall here, and this is a space, so this is a cavity. Okay, so what I would do is to go down beyond the slab, and then go that way. And then from that way, we can go horizontally, and eventually we have to go down somewhere. So what can we do here? If we are on this 15 level, So how many stacks are we going to have? That's a good question. I would say we can have either one or two, but for sure we need we need a stack for the toilets and we need a different stack for the sinks. Okay, so yeah, let's have only one. But if we have only one stack for 8 toilets, I think it would be better having one here instead of having one there, because we are connecting, we have a long horizontal branch. So the horizontal branches have to be as short as possible. Okay, so let's do it. So we have to go down from these fixtures, from this drainage. So we draw pipe, and now we can do the same. We have to change the elevation. So the elevation is not 0. We can go negative 2 feet. There you go. Okay, so there will be a vertical stack here. And from this one, we can draw pipe. We change elevation, -2. And well, I'm not connecting this because eventually I need to. And then if I want to connect this, I can draw pipe. If I know the elevation, I can make it -2. And just remember that for this, for the drainage, I only need this 45-degree angle. So the first one, well, even for the first one, let's do it better. So let's make this 45 and then this one. There you go. And then on the 3D view, yes, it works. Okay, so we have those pipes. And now you need to connect this one and this one. And for the vertical one, we can work with the north elevation. And you know that from this one, we need to draw pipe. So we need both. We need a vent stack and we need to, this elbow is not here. And then we need to go down beyond the first floor slab level. And now we are in the basement. And usually we don't go down the basement. We can go through this from the basement ceiling all the way out of the building. And what we have to do now, we have to draw a pipe with 45 degrees. Okay. And you see that when we have this, the size of this fitting matters. Okay. Because if I want to connect this now with 45 degrees here, it doesn't work. So what we do is to draw a pipe. There you go. You see? So those things are complicated because maybe there's another fitting with 2 openings, like with 4, 1, 2, 3, 4. But I don't like it. Okay, so having a fitting with a lot of pipes connected, I don't like it. So I think this is better. Okay, but you have to design it, and then you have to dimension the vent stack, and then you have to dimension this waste stack. because we still have to connect. Probably we need to go farther, and then we need to extend this until the end of the, okay, so here outside the building there will be the public sewer or sanitary system. Okay, so that's the, we have different options. If we connect all the toilets to the same branch, horizontal branch, and then we have the stack, the vertical stack at the end, there is a lot of horizontal distance and it's not good. So the shorter the horizontal branch, the better. So that's why I've decided to place the stack here. Okay, and now we will need another, so this is the vertical one, yep. And now we will need another vertical one here. So the criteria can be the same. So you can connect all those to this point or here, and then this four to this one, this four to that one. It's up to you. But it's important that if I check the elevation, the drainage, remember that we need to insert a trap. Okay, and remember that we have to go beyond this level, the slab level, and because we cannot break the slab from the structural point of view, that would be a disaster. Okay, so it's kind of fun. Okay, so here we have a mistake. Okay, so this is what you have to make sure that it's not happening. You see that there's an intersection between the vent stack and this, so this can't happen. So we can drag it. There you go. Okay, so now it works well. So be careful with these kind of things because this is a terrible mistake. If we have an intersection between pipes, water pipes, stacks, air ducts, that's okay. And so when it comes to calculations, I think we are done. You can take this number for granted, so you can design 4 storm stacks, and then you only have to let me know the size of sanitary branches and vertical pipes for the sanitary and for the gray water, and then the size of vent stacks. We did this a week ago or 2 weeks ago, I don't remember. So try to do it. If you don't remember, get back to me. I'll explain to you again. But now we have to check if the size of those stacks are according to our Revit design. Usually the vent stacks are what is 4. I don't think we need 4. Probably 2 1/2 would be enough. But probably this is 4. I don't know, maybe we need a bigger one here. It depends. Okay, and finally, well, finally, or at the beginning, I don't know, you can start by doing, so let's start with the calculations of the mechanical system. So calculations with the drainage or the water supply, we don't have to calculate anything. We just have to count the fixture units, and then we have to check the table if the diameter is the right one, or we have to make it bigger. That's the only thing. But when it comes to the mechanical, we do have to calculate something. So since we did this at the beginning of the course using this Excel file, So I'm going to do it again so that you can refresh your memory. Okay, so first we have ventilation airflow. So for the ventilation airflow, we need to get to know the building. Okay, so there's a educational building. We have classrooms here. We have the first and the second floor. They are both the same. So the classrooms have 20 plus X. So again, so I want you to have different numbers here. So this X can be one of the team components last figure. The ID is last figure, okay? So it can be from 20 to 30. So this is the right size for this classroom. And then we have offices. So in those offices, we have 4 people. And in this large office, we have 6 people. Okay. So here you don't have to, these numbers will be the same. And then we have a schedule. So the schedule, the classrooms, they are with full occupancy 20 or 25, 30, 29 maximum. People from 8 to 1 p.m. and then from 3 to 8 p.m. So if we have 20 people times 20 CFM, so this is 400 CFM per classroom. Okay, so this would be 400, 400, 400, and here we have 4 people times 20 CFM. So this is 80 CFM per office, and this one is 120. Okay, so how many classrooms do we have? 6. So the total CFM, it's 6 classrooms times 400. So this is 2,400. Okay, so let me write down. So the classroom, the total CFM, it's 2,400. And for the office, it's 80 CFM, 1, 2, 3. So there are 6. So 80 times 6, it's 480 plus 2 times 120. So this is 720. The CFM and CFM. So this is for the classroom, and this is for the office. So now if we want to calculate the heating loads, we have to change the number of people. So according to this schedule, so offices are operating from 7 a.m. to 8 p.m. and classes as of 8 a.m. Okay, so the first hour from 7 a.m. to 8 a.m., we have only people in the office. So from 6 to 7, we don't have anything. 0. And here from 7 to 8, we have only 720. 720. Then from 8 to 1, it's 2,400 plus this. So that equals this plus this one. Okay, 3,120. So this is 3,120. And this is from 8 to 1 p.m. Then from 1 to 3, it's only 720. From 1 to 2, from 2 to 3, And then the rest of the evening or the afternoon, it's 3, from 3 until 8. There you go. Okay, so this is the schedule. Then we need the total ventilation load. I haven't changed the indoor temperature. Indoor temperature, this is comfort temperature, so it can be indoor temperature and relative humidity can be 70 and 50, but I haven't changed the outdoor and the relative humidity. So here you have to type the temperatures that we have in winter and then in summer. Okay, so you have to do it twice. So after doing this, we need to create the graphic. So I will remind you of how to create the graphic. So we know that at least we need to relate outdoor temperature and energy. Okay, so let's select this column, insert recommended charts. So we can use this one with lines. We click OK. Okay, so here we have the temperature. Now we have to insert the energy. Okay, so right click here, right click, select data. We have to add the series name is energy. The values, all this column. We click OK. We click OK again. There is something wrong. Select data, this one, edit. Okay, we need this. So it's all this. Select data, add series name. Yeah, I know. So series name is the energy. This is the X values. I did it wrong. So we have to select this. And the Y values, it's the column. Okay, now it works. Okay, and if you remember, here we have the energy and here we have the temperature. The energy ranges from 0 to 8 million, and the temperature ranges from 2 to 15. Okay, so that's why we have to select the temperature, right click, format data series, and we have to select secondary axis. There you go. Okay, so now we have the outdoor temperature, and the values of outdoor temperature is from 0 to 25. And if you hover the mouse here, you see that at this point, the value is 21 Fahrenheit. And if you click here, the value it's 6,069,000, whatever. So you have to relate outdoor temperature and energy consumption. The energy consumption is related to the occupancy. When we have full occupancy, we have more energy consumption. And when we have lower outdoor temperature, we have a higher energy consumption. So that's why I want both graphics, because the occupancy and the outdoor temperature affect the energy that we are consuming. So this is that's it. I mean, we don't need any other calculations for the ventilation airflow. We have already calculated the ventilation airflow. The indoor and outdoor enthalpy, it's here. Okay, so this is the indoor enthalpy, and this is the outdoor enthalpy. So just by copying this table, okay. So on this table, we do have the indoor and outdoor enthalpy. There's an indoor enthalpy because the indoor temperature doesn't change, but for the outdoor enthalpy, since the temperature and relative humidity are changing, the outdoor enthalpy will be changing as well. This is the number of people, the total CFM. By changing the number of people, automatically the total CFM changes as well. And this is the ventilation load. So we need two things. We need the total energy, and the total energy is this value. So I didn't copy. Okay, this is the total daily energy in BTUs. And the ventilation load, we need to, because we want to dimension the system now. So we have to select the highest value here. So which is the highest value? Ventilation load 15606,566. Okay, I think it's this one. Is 6,006,087 or 687,415 BTUs. Okay, so let me write it down. 6, 7, 1, 5. Total ventilation load in winter, then you have to do the same for summer, will be 6,687,415 units BTU divided by hour, because the ventilation load, the energy, it's BTU, but the ventilation load, it's BTU hour. So this is power. Okay, so now we have this, the heating power in winter. Well, that would be the heating power in BTU hours. And now we need the cooling power in summer. So you only have to type these temperatures there, and you will get the power, the cooling power. What else do we need? The daily energy in summer and winter. So this is the daily energy. This is in winter. And then you have another, you need another table in summer. And here you have to insert the this graphic. $6 million. Yeah, we are changing the number of people. Okay, the total CFM, it's just 20 times the number of people. Okay, so I think I did it wrong. You are right. Okay, so yeah, it's good that you are watching the lesson and you find out that I made this mistake because we are changing the number of people. Yeah, so I have changed the CFM, but we are changing the number of people. So this is the total CFM. Yeah, so I did it wrong. So the number of people here. Yeah, so it's 20 times, it's 20 times 6 classrooms. And this is 1, 2, 3, 4 times 6 and 6 times 2. So this is 12, this is 24, and this is 120. Okay, so it's 36. So the number of people is 36, 36, and for full occupancy is 120, 156. Okay, thank you, Tyler and Erin, because this is the right, yeah, I changed the CFM, but we have to change the number of people because we have this column here, so it's calculated. So now the maximum power it has changed is 300, 334, 370. Okay, so that would be 334, 370 BTU hours. This graphic, no, it's not the right one. And this table has changed as well. This total. There you go. This is the daily energy in winter. And this is the ventilation load. And the maximum ventilation load is this one, 334,370. Okay, this is the chart. So this is what we have to do in winter. And then we have to do the same in summer. We are not changing the number of people. And we are changing just the indoor and outdoor temperature here. Okay, what else? Um, what is the total daily? Okay, so we have already done this. And now what about the schematics? Well, I want to explain this because as you have seen in this building, we have different, okay, so how does it work? We need to understand the building. So what are the elements that we have? We have a mechanical room, the basement. So in the mechanical room, we have a domestic hot water heater and an electric water heater. So what do we need two water heaters? So one is for domestic hot water because the temperature of domestic hot water, it's 140 Fahrenheit because we need to kill these bacteria. I think I've talked about this before. Pneumophilia, Legionella pneumophila in Latin, and temperature. Okay, so between 25 and 50 Celsius is the optimum temperature for this bacteria to grow and to reproduce. So what do we have to do? We have to go beyond 50 Celsius. And so the temperature is always 60 Celsius. So we have to to Fahrenheit. Okay, so around 60 Celsius, it's, yeah, so I wasn't sure. It's 140 Fahrenheit. Okay, so the temperature here is 140 Fahrenheit. But the water heater that is connected to the air handling unit, to this coil, it doesn't have to be at 140 because this water is not in contact with human beings. Okay, so we don't need to heat up this water up to 140. We have to heat up domestic hot water, the water that comes from the sinks. Okay, so we need 140 because it's in contact with people. But the water that it's inside this circuit from the water heater to the air handling unit, we don't need to connect, or we are not in touch, or so we are not in contact with this water. Okay, so that's why we need two different water heaters or two different tanks, one for the domestic hot water and the other one to heat up the air of the air handling unit. Okay, so this is the first thing we need to understand. Here we need two water heaters. You should the size of water heaters. We are not calculating the size, but we need both. Okay, we need two of them. Okay, so on the Revit file, on the basement, if we insert, no, if we go to systems, mechanical equipment, there should be storage tank. Okay, water heater. Gallons. Since we are using or we are designing a big building, so select either the 75 or the 100 gallon. Let's select the 100 gallon. And then we need to place two different water heaters in this mechanical room. Okay, so one of the water heaters will be connected to the domestic hot water, and the other water heater will be connected to the air handling unit. Okay, so at least we need two water heaters here. 3D. What about the orientation? Well, we need to find out. So from this, we have the inlet, and here we have the outlet. Okay. So you know that we have, well, we will talk about this later, because now this is the hot water supply. So we need to supply, and then we need two pumps. Okay, so I don't want to explain now how to do this. I wanted to explain, so this is for the domestic hot water, okay, for the sinks, but I want to explain this one now. I want to connect this water heater to the air handling unit that should be placed here, here on the 3D view. We see the shafts, okay? Of course, those shafts, we need a cap for those shafts, but so far we can leave them open because there will be a lot of pipes and drainage stacks and air ducts going out. So we need now to connect this water heater to the air handling unit. So we should place the air handling unit on level 30, hidden line. Okay, so this is the roof, and we need to place the air handling unit, but we have to be careful because we have those shafts. So if we place the mechanical equipment, where is the air handling unit? Here, air handling unit, 10 square feet, I think should be enough. Okay, and now how do we place this? I don't know, because okay, so this is the supply shaft. Yeah, so we need to minimize the air ducts. Okay, so let's try. Okay, so now what do we have to do? We have to connect this water heater to the heating coil of this element, of this air handling unit. Where is the heating coil? So you remember that we have two coils here. So we have 1, 2, 3 inlets or outlets. This is the cooling coil. When we have only two, this is the heating coil. So this is inlet and this is outlet. So if we draw a pipe here, we need to connect this inlet to the outlet of this element. Okay, so through this shaft, now we have to go down. We can go down just by changing the elevation. So we can click here, -20. No, it's not enough. Let's say -30. Are we on the basement? No, let's say -35. Okay, I think now we are on the basement. So let's make it here. And if this is the water heater that we are using for, okay, this is inlet and this is outlet. So since we have connected the inlet or the outlet, okay, so this is the inlet. We have to connect this to the tank outlet. Okay, so this is the outlet. Draw pipe. middle elevation, let's make it 7. And now from the top view, there you go. Okay, so the water heater outlet is connected to the air handling unit inlet. And now we have to do the other way around. We have to draw a pipe. We can change the elevation, let's say 2, 1. And then we have to go all the way parallel to this. We change the elevation to -35. And now we have to connect this one, this inlet, draw pipe, change the elevation 5, 6, 7. To this direction, and then from the top view, there you go. Okay, so the only thing we have to make sure is that the vertical pipes are in these shafts. Okay, so we are not free now, so we cannot connect these. No. We have to make sure that those pipes, especially in the vertical one, are going through the shaft. Okay, so now we have to connect. This is the water heater, so that heats up this water, and then here we connect this to the heating coil of the air handling unit. We should do the same with the cooling coil. So now we have to place on the roof. What do we need? An air-cooled, I think it's specified here. See, we need an air-cooled chiller. Okay. So now we need an air-cooled chiller on that ceiling. So do we have mechanical equipment? Do we have condensing units, cooling tower, outdoor? Okay, so here we have the air-cooled chiller, always the smallest one. And where? Since we have to connect this and this, so let's place it here. And now we need to find out where do we have these connectors. Okay, so we have inlet and outlet. So again, now you have to connect the cooling coil, the inlet to the outlet, and the outlet to the inlet. Okay, so now we have the air handling unit and the air cooled water chiller. So yeah, so this is the inlet. So from here, we have to draw a pipe. And from there, we have to draw another pipe. Okay. So now you have to figure out how to connect these two pipes to this cooling coil. Okay. And what's next? Okay, so now we have to work with the air ducts. So I'm going to do it. I'm not going to finalize it, but I want you to, because especially the supply, we need to go through this shaft. As you can see in these drawings. Okay, so this is the supply, and then we go down through the shaft. And then from, this is the shaft, this is the vertical pipe or duct, and then we go horizontally here. We don't have a lot of CFM, so the ducts are not going to be huge. I mean, you have a, because this is an actual building, and so you see that when we have these branches, because we need to supply air to the office, since in the office we have only 4 people, this, look at this, it's very thin. Okay, so, but we need a supply diffuser and we need a return diffusers. Okay, so let's do it. What size? So this is 65 times 40. Oh, this is too much. So let's edit the type and let's make all of these 20 by 20. I think it would be more than enough. Apply. Okay. So I want this to be, maybe it's 30 by 30. I think 20 by 20 would be enough. So now we can draw this duct. But I want this to be round. Okay, round is better. And now the only constraint is that we need to go this way. And now we can change the elevation. And we can go, let's say 15, no more, negative 17. And then probably I need to go this way and then that way. Let me see what I have done. Yeah, it works because I have to make sure that it's just under this level. Okay, so it's below this slab level, and now it works. So it's just here. Okay, so we have to extend this up to the final classroom. And on this, on level 0. Oh, so you see, it should go here within the corridor. Okay, that's better. And now we need to place the supply diffusers. So we have a supply and a return diffuser. So we can go to air terminals. We can supply with 8 neck. So the first one can be here. Second one can be here. And the third one can be here. So that. And what about the elevation? I think I didn't change the elevation. Yep. So you see this, I have to change the elevation of these diffusers. So let's make it 10. Yeah, 10 feet is enough. Okay, so now I need to connect this one, draw duct to this one. Oops. Too small. Flex duct. Okay, I didn't select the flex duct. Okay, so now you have to connect this and this. And since we have on level 0, yep, we need supply diffusers for the okay, we can copy because we need supply diffusers here in this in the office space. So we can place this here and here and here. Okay, so now we have to connect this diffuser to this duct and this to this duct. Okay, so working with T's and flex ducts, it should work. So that's it. Okay, so this is, I think we are going beyond the first assignment because now we have shafts. So the architect or the design department provided us with this file, and now we have to abide by the shafts and all these vertical elements that we have in our building. Okay, so we're not free designing especially the air ducts. So if we have this vertical shaft, we have to do it. If we have this for the pipes, so we have to go for this one. And then for the supply, for the return diffuser, so this is the supply. You have to do the same. Okay, so you have to do the same on this floor. So once you are done with this all horizontal duct work, you can copy and paste it here on the first floor, on the second floor, sorry. And finally, you have to figure out how to work with the diffusers. The option in this drawing, you see that we have this supply diffuser here. If we zoom in, if there is an arrow going out, this is supply diffuser. If there is an arrow going in, this is the return diffuser. And as you can see, there are two vertical pipes, and they are here. And then on the roof, we have two vertical pipes, then we have this T, and then we go to this element. Well, this is up to us. So that's why we have all these shafts here, this one, this one, this one. But you have to figure out you have to place a return diffuser in the classroom. Okay, so each classroom, you need a supply diffuser and a return diffuser here. 1, 2, and 3. And in each office, we also need a return diffuser. Kind of. I think, okay, I have to change the elevation again. What was the elevation of this? This 10. Okay, so I think I can select all these. And change this to 10. All these. Change this to 10. Okay, so now we have to create another, um, so it comes from this point. This is the inlet return. So we have to draw duct. I want the default round one. Change the elevation. Let's make it 6. Draw duct. Round. Elevation 6. What's going on? Well, I'm not sure how to do this. We have shafts, so we can have a vertical one here and connect this, or we can have a vertical one here, and then we can connect all those. I don't know. You have to figure out. But that's the idea. Now we are not free, and we need to work. We need a supply and return diffusers in every classroom and office. But now we have to connect. Yeah, so I think this is easy, but the return, I think it's going to be more difficult. But well, try. Okay. So we have been like an hour and a half working on that, or I have been working on that, and we're almost done with the assignment. Well, we're almost done. So everything is here. Calculations are almost done. The Revit file, yeah, you need to work on that, but you have 15 days. And in a few hours, you can complete this assignment. The difficult thing is to get to understand the building. So that's why I wanted to show you all the components of the building. And we are not done yet, because now we have to insert the last thing is so you see that we have other heat pumps here. And on the classrooms and the offices, we have these green rectangles. So this is a split system. Okay, so it's written here that we have a split system with an air-to-air outdoor unit and indoor unit with ducts. I will explain this on Thursday, but it's like a backup. Okay, so we can have all the heating and cooling systems with the air handling unit. This is an option, but sometimes we need a backup because if something is going wrong, if the heating or cooling coils of the air handling unit are not working well, or we have an excess of heat because I don't know, this is something that it's not that hasn't been foreseen, and we have something that okay, so we need a backup plan. So each classroom, as you can see, there are two systems. We have the air handling unit with the return and supply diffusers, and we have these split systems. So if you look at the TDS center, we have the same, and this is an educational building. So this is the usual strategy. We can provide all the heating and cooling with the air handling unit, with the air chiller and the water heater. But if something goes wrong, we need a backup system. So here, the backup system is the outdoor heat pump and indoor split units. Okay, so in the TDS center, we have both. We have the air handling unit, and we have split systems just in case. Okay, so it's good having two systems in the same classroom, especially in these kind of public buildings with a lot of, they are complicated because we have a lot of people. The occupancy can be different in different classrooms, and sometimes one of the classrooms is full and the other classroom is empty. So one of the temperature that we need in this classroom can be different than the temperature that we need in this classroom because of the occupancy. Okay, so that's why having two systems, uh, it's more expensive, it's more complicated, but we gain flexibility because we can, having two systems, it's better. Okay, so and usually we have the air handling unit because we need ventilation. So the air handling unit ventilates or the fresh air, the building. If we attach or we connect the air handling unit to the water heater and the water chiller, that's fine. So we need a ventilation, a heating and cooling system. But in addition, we can use the backup system with splits. Maybe those splits are working only a few days a year, but when they work, you notice that they are working because it's okay. And